now we're going to move to the demo. And as I'm assuming most of you know GeoDa, what you might not know is the philosophy behind GeoDa. It's really designed as a teaching tool, but it's also obviously a research tool. But it's designed to facilitate a progression of exploration. So you start, as I like to put it, with just looking at the data, making simple maps, simple graphs, looking at connections through brushing and linking, then moving through more formal visualizations, doing cluster analysis, local clusters, looking for patterns in the data a little more formally, possibly dimension reduction, regionalization, and that is the process of hypothesis generation. And then you move into the spatial regression to do the hypothesis testing. So our goal, our ideal is to discover the unexpected, but in the fall, I'm sure Julia will give a talk illustrating how that works. And then what you may not know is that GeoDa is now, comes with language customization, and we have English, simplified Mandarin, Spanish, and Russian. And Anaïs, we're just waiting for the French version. Okay, let me switch out of this and into GeoDa. And I have a whole list of scripts so I don't get lost, because I tend to get lost in these things. Rather, I tend to get carried away. So I'm not really lost. I just can't resist. So just to get started, we'll do a map of, well, I'll show you the data set. So what I've done ahead of time is turn these three variables, crime against persons, crime against property, and donations, into standard normal variates so that I can compare what I do in the various clustering things. And then I also created a constant, and the constant is to be able to cheat in the bubble chart, as I'll show you later on. So just to illustrate what I mentioned in the talk, if we do a box map of each of these variables, you will see very little overlap. Now, one thing I wanted to point out, but I don't have time to go into it, but if you haven't used GeoDa in a while, this is a new feature, and it allows for multi-layer analysis, which is a first. There's still only one active layer on which selections and so on work, but it allows you to put points on top of polygons or regions on top of, like, we could have multiple regions. Let me just show you. Oh no, it's too hard. But so the other thing that I wanted to mention, and I don't have time to go into it, but the tools now have a number of GIS functions, namely a spatial join, which is essentially point and polygon, which is very powerful. A dissolution, dissolve, so grouping, say, the departments by region would be with dissolve. And then, let's see, what was the other one? So we have aggregation, and we have merger, and I'll think of it. There's another one that I wanted to mention. But so we have a little bit, oh yeah, we have in the saving, so if you save, save as, see this here? You can save with a projection, and this is actually a way to change projection, because by clicking on this little globe, you can load your CRS from a source, and then it converts the data, the map, to that new projection. So this, I think, is by far the most intuitive way to switch projections when you have mismatches. So these are some of the new kind of mini GIS features, but okay. So we have our box map, but because we're working in 3 dimensions, we can actually see these variables, the data points, I mean. So we do a 3D scatter plot, and we have the points floating in 3D space. So you can move around with this. There's some issues with the zoom that we have to figure out, but you know, basically you can see them, right? And so now we can start thinking about what does close in attribute space mean? And what do we possibly give up when we work in 2 dimensions? So let me do a simple scatter plot between these 2 variables. I'll get rid of the regression line, so we just have the points. So let me rotate this just a little bit. Yeah. So let's take these 2, you know, very close in attribute space, actually not that far apart in geographical space. There they are. And if you project them to X, Y, you see behind there, they seem super close, right? In 2 dimensions. But keep turning, and that's actually an artifact of the 2 dimensions, because they're pretty far apart when it comes to the 3rd dimension. So what I like to do is to illustrate all these concepts. It's, let's see, there's, yeah. So these 2 are close geographically. And no matter how you turn it, they're also very close in attribute space. So those are the ones we want to find. Those are the ones, those instances are what we want to discover. So locations that are neighboring and are also super similar in attribute space. Now, I wanted to show these 2. And those are also very close. Now remember those 2, they'll come back later. Okay. So quickly, the distance scatter plot is here. We used to just have the correlogram. Now we have the distance scatter plot too. It's pretty straightforward. I'll just show you for these 3 variables. You pick which distance you want, Euclidean or Manhattan. And then just following geostatistical practice, really what you should do is take a practical distance, or the distance of relevance, where you take half the bounding box diagonal. Otherwise, you have a lot of points that are very far apart. And these are a lot of points. You know, there's 1,800 points for just, you know, out of 3,500, basically, for just 85 observations. So when you go to 3,000 counties, this blows up very quickly. And then we use a scheme that we also have in the correlogram, namely, we take a random sample of the points of the distances to fit this curve. And this was originally developed by Mark McCann at ASU, and it works really fairly well. So, so we have this curve, you know, it's flattening a little bit. It doesn't look quite the same as the one on the slides, because you can adjust the ranges, and then it looks a little bit more like the one that we had in the slide. Yeah. And so that's very simple visualization. I personally don't use it that much, because I don't usually look at global statistics. I focus on the local. Okay. So here we go with the local. This is where there are quite a few differences depending on when you last checked in. Let me just point out the newer ones. This is very new. This is not in the official release yet, as far as I know. This is so the local Moran psi, in essence, compares the value at a location with the average of the neighbors. And so the median local Moran psi compares the value at a location with the median of the neighbors, which corrects a little bit for the effect of outliers. Now, outliers, if you do this a lot, you sometimes find very strange results, and almost always these can be related to outliers where you have so one very high value and then a bunch of very low values, and the high value pulls the average way up and gives you a significant cluster, whereas it's really not that significant. So that's a new thing. These are the joint count statistics, the univariate, bivariate, and collocation, univariate and multivariate local Giri, and then this is a new one, the local neighbor match test. So let me just show you a couple of these. So we start with the k-nearest neighbor weights. And let me show both of them. We're going to do the max in terms of randomizations. And then I like to turn the number of filters down. So that's just your classic local Moran. Then the median local Moran, same variable, same weights. We're going to crank it up and do the same filter. So the comparison between the two, there are quite a bit of similarities, but overall, there are fewer significant locations with the median local Moran. So that may point to the sensitivity or to the effect of some outliers for some of the other values. We go from basically 16 quote unquote significant locations to 7. So that's quite a drop. So I think it's a useful thing, as I like to say, when you use the local Moran, don't get carried away, keep it in perspective. That's why I like to do a lot of sensitivity analysis, try different weights, different p-values, Bonferroni bounds, all these kinds of things where, if you do, this is the art part of exploratory data analysis. If you do enough of this, you start seeing some patterns emerge, and ideally these are things you didn't see before. Most of the times these are things that you already knew, but that's the name of the game. So then comparing local Giri, we see that there are some differences. Let me just put it down here. So the local Giri picks up different types of similarities. Some are common, like this one, and some of them in here, but many of them are not. And so it really picks up a different kind of similarity. And one way that I often interpret this when people ask me, well, which one should I use? You know what my answer is going to be, both. And because they pick up different things. So Moran psi, as I mentioned earlier, is very much a cross-product statistic, which is really about linear association. And so we also see that when we use the Moran scatter plot, there's a line there that's a linear association. In Giri C, there's no such thing. It's not a linear association. It's actually nonlinear because it uses squares. So that's a different criterion for similarity. And so just like you might have different results when you use different spatial weights, which are different definitions of geographic similarity, you will have different results when you use different criteria for attribute similarity. So there's nothing wrong with that. Just to show you some of my frustrations with the multivariate local Giri, now we take all three variables and do the same thing again. So first of all, this is not useful because they're all the same, but this is. So this is the multivariate local Giri significance map. And guess what? So this and this one are the two most significant locations, and they are in fact these locations. And to illustrate what is going on, we can show the selection and the neighbors connected. And then a cool little thing that Jun added is we can customize this. We can change the thickness of the line, and we can change the color. And you can even change the size of the balls. So then when you go back, you can twirl around and really explore, you know, how do these neighbors in geographic space connect to locations in multi-attribute space. And so one thing that I found very encouraging, because I had never really looked at this before until I taught one of my workshops and decided to do it with 3 variables instead of with 6, because then I could see it in the 3D scatter plot, is that this, I mean, this is not nonsense, right? So you might say, and some people have said this, yeah, this is just, this multivariate local Giri is just picking up random things. It's not really meaningful. But if you drill down fine enough, you know, these two that are the most significant are in fact very close in attribute space. So it is picking up something that is actually meaningful. Now, you have to make the jump, right? Now we could still see it. If we work with 10 variables, we can't see it anymore. So then we have to take a leap of faith that it still does the same thing, right? So, okay, so now let me first show you, let me get rid of a bunch of these because it's gonna start getting very cluttery. And I just want to keep this one, the multivariate local Giri. Okay, so now I'll show you the local neighbor match test, first manually and then more directly. So we're going to make a new set of weights, and this is new. I don't think this might not actually even be in the current release. But when you do distance weights, since I always work with the development version, I have no idea what the actual release is. You can do distance weights based on variables. So the old way was always centroids and then either use arc distance or Euclidean distance. Now you pick variables and you can transform them or not, and then you can do Euclidean or Manhattan distance. So now I'm going to take my 3 variables. So and specify k nearest neighbors, 6 k nearest neighbors. So these are the 6 nearest neighbors of the observations in the cube, in the 3D cube, in attribute space. So So now these weights are in the weights manager. So because we have them in the weights manager, we can pick the k nearest neighbors distance weights and do the weights intersection. And that's a new weights file. Now we have this one, and we can look at its distribution. So this shows how many neighbors are in common between the distance 6 nearest neighbors and the multi-attribute 6 nearest neighbors. So when you do this histogram, you can save the connectivity to the table. And I'll just leave this for now. So then we go to our table. You see this has been added at the end, and you sort this, and you see there are 3 departments that have 3 out of 6 neighbors in common. Right? So one of these is, again, highly significant in multivariate local Giri, but one is not, and one is somewhat. Right? So now we can, so now you get the idea of what's going on. We can map this unique values map on our number of neighbors, okay? And then we can superimpose the graph on top of it, and you can make the graph, you can make them thicker, and I always like to make them red so you can actually see them. Okay. So now you see what is going on. You see that there are 3 lines going out from here. Now, sometimes this is a little counterintuitive because you have to remember k nearest neighbors is an asymmetric relationship. So B being nearest neighbor to A doesn't mean that A is nearest neighbor to B. But now with these 3 selected, we can go back here and we see what is going on here with the nearest neighbors. So these are the 3 neighbors that are in common between geographic space and attribute space. And this is where you see, I mean, if you look at this carefully, you see some weird stuff, right? You say, well, look at how far these are. Well, that's part of the, spare space, empty space phenomenon in high dimensions. So for this point to reach its next nearest neighbors in attribute space, it has to travel quite a bit. So that is something you realize when you start looking at these. Of course, with higher dimensions, you can't do it anymore, but I find it very insightful to look at this in the data cube because you can actually see it. So the problem is this map is not very nice. So then instead, we do the local neighbor match test. We pick our 3 variables. Euclidean distance, you can change this to Manhattan. And same with the geographic one. And then we run this, we can save these 2, and we have our map with nicer colors. And then in addition to the map, we have and this is always a little tricky. So you see these numbers match, obviously they should, but we also see that the chance of having, the probability of having 3 neighbors in common out of 6 is less than 0.01. So that's 0.003. If you do it with 6 variables, you actually have one that has 5 common neighbors. So that's pretty interesting. So this is the local neighbor match test, and this is my latest favorite. So in terms of intuition and visualization, especially when you can't do the 3D scatter plot anymore, I really have been using this a lot, in also with much larger data sets. So then the last, well, how am I doing? Yeah. So nobody's going to get to ask any questions. This is where there's a lot of changes. Not so much to the menu, but to what is going on under the hood. So the only really new thing recently is this TSNE. So it stands for Stochastic Neighbor Embedding. Skater, Redcap, and MaxP have been in there for, I think, a little over a year. And then HDB Scan and Spectral also probably a little over a year. But multidimensional scaling. So the it makes a distinction between 2 algorithms. And one is the classic metric, which is basically, if you do the linear algebra, very similar to principal components. And then the other one is called SmackOff. And I forgot what it stands for, but it's something of some complicated functions or something like that. So the idea is to approximate a complicated function by a simpler one that what is called majorizes it. So it's always, if you minimize, it's always on top of it. So the way to think about that is, let's say you have like a squiggly curve and you approximate it by a parabola. The parabola touches the curve, and then you can find its minimum and then get a new parabola where that touches the curve, and you keep moving. And if all goes well, you reach the minimum that is very close to the minimum of the true, much more complicated curve. In my latest lab notes, which aren't released yet, this is all explained in glorious detail. So the classic metric has one option, which is to use power iteration, which doesn't really make any sense for this data set, but if you have very large data sets, it does make sense, because the difference between principal components and multidimensional scaling is, in principal components, the eigenvalue calculation is done on the dimension of the number of variables. In multidimensional scaling, it's done on the dimension of the observations. So if you have very large data sets, those are very large matrices, and you really don't want to compute all these eigenvalues, since you only need the first 2 for a 2-dimensional representation, 3 for a 3-dimensional representation. So we'll move to 6 variables now. And we'll use the power iteration just for fun. One new thing, which is may not be in the official version yet, I can't remember, is that we can now show this in 3 dimensions. So we run this, we get 3 new variables, and these variables are shown in 3 dimensions. So these are now 3-dimensional points representing a 6-dimensional attribute space. So again, we can look at the neighbors and all that stuff. The summary characteristics, this is actually not an exact science. So the stress value is the difference for all the distances between the distances in the original space and the distances in the reduced space. And that is the objective function. And because it squares that difference, it tends to favor doing well for the large distances because they give the biggest penalty, right? So it doesn't do that well for the smaller distances. Another measure is just a rank correlation between the distances in the original space and the distances in the small space. In this case, this is pretty good. But again, these are global measures, which are not necessarily that great for our purposes. So that's the 3D multidimensional scaling. SmackOff has a couple of parameters to set. I'm going to do it in 2 dimensions. And this is just, you find the neighbors, close neighbors in this 2D space are also close neighbors in high dimensional space. Stress value is poorer, the smaller the better. Why? Because here you have 3 dimensions, here you only have 2, but the rank correlation is not that much worse. So this is SmackOff. The new one, so I won't, I have some other things here, but I'll skip it. So the new one is TSNE, and TSNE is a totally different animal because it does not minimize what is called a stress function. So this difference between the 2 sets of distances is called a stress function. TSNE minimizes an information criterion that has to do with the probability distribution in the both dimensions. And it's kind of complicated. Essentially, it's a kernel type of thing that uses distances as a standard to determine the variance of the kernel. And it tries to match the distribution of the points in high dimensions in low dimensions to high dimensions. So there's a whole bunch of parameters here, and they're very complicated, Perplexity basically means the average number of neighbors. This is a way in which the computation is sped up. In the lab notes, it's all explained in detail. The learning rate is how much attention you pay to the gradient itself, the partial derivative, the direction of descent. And then the momentum is how much attention you place into the last changes. So all these things are there because this algorithm, it's a very nonlinear optimization, tends to be trapped in local optima. And so it's a very different kind of optimization in that it doesn't minimize an objective function per se. It sort of does, but that's not really how it stops. It stops when the points don't move anymore. And let me show you this. So first, I'll just show you the default, and then I'll show you the cool way. So this is the default, and very quickly it reaches a stability, right? This is the speedometer. So you reduce the speed, and then you can see what is actually going on. And so you see that this tends to be trapped in local optima. It moves around, and then all of a sudden it will go poof and move out of this local optimum into something that is much more stable. There you go, see? Jumped out, and now see how the iteration, the error goes from 52 to 1.4 to 1.9 to 1.5, 1.3, 1.24, we're basically done. It just doesn't move much anymore. So then, you could stop this, and you could stop it at any time. So if I have time, after I'm done, I'll do this with the US data. It's spectacular. So anyway, same thing. You can then, if you stop it, you can save the variables, and then you can link and brush to see the extent to which, close neighbors are also close in there, or for neighbors that are far apart are also far apart. So this is on a different scale. This is 5, this is 3. So you adjust the scales to make it comparable, but that's how you can then kind of go back and forth. The moral of the story is don't do this mechanically. There's a lot of stuff going on. Each of these algorithms has its advantages and disadvantages, so you have to have a good sense of what it is you're looking for. And one other feature that is implemented here is that you can see what happens to subregions. So a lot of the rationale for multidimensional scaling is to find clusters in the data, right? Points that are close together. The classic iris example that R uses all the time, you know, where you see the points in different parts of the graph and they're one type of flower. So now we have the 6 regions. So let me show you. So these are the 6 broad regions that Giri has in his original data set. So we are now going to see where those regions are during the optimization process. You know, you see them jumping around, and then around 500, it'll stabilize. I mean, I could speed it up, you know. So now we have these regions, right? So I think I already saved them. How could we visualize that? Because the scatter plot doesn't show any colors, and this is my trick. X-axis is, you know, the first one. Y-axis is the second one. Bubble size constant, and the color is the region number. Okay. So because the bubble chart by default does a standard deviational lap, first thing you do is change this to unique values. And we have our regions again. And then the next thing you do is to adjust the bubble size. And now you can link and brush, you know. Now you can see where are these in multidimensional space. And same thing, you know, or actually, I think it's these guys. So this again is a way of showing the tension between the two. So the final thing is the regionalization. I'll do it real quick because I think I am running out of time. Let's see, where am I? I'm going to do a k-means on these coordinates, 6 clusters. And so here they are. So then you can do the same thing and showing the, in the bubble plot. Where is my bubble plot? So now instead of the, oh, I have to do it again. So the bubble chart, same 2 once, but now the variable is the cluster from the k-means. And so you see these are nice and compact regions in multi-attribute space. And then you can see the extent to which they are here. And then you can do the reverse, you know, do a, scatter on the 6 variables. 6. Make sure you have the queen weights or it gives nonsensical results. So here, and then you can again do the bubble chart. But now, let's see. Yeah. with these two. And now the variable is the scalar cluster. And again, you can link and brush. You see some of these, like this one, doesn't sacrifice too much in terms of multi-attribute similarity, but the others, are more all over the place. Yeah. So you can, the reason I use the Giri data set is because you can really see something. With larger data sets, you have to spend a lot more time carefully looking at the graphs. And so let me just, so I'm going to do TSNE. So I have a bunch of variables here. We set everything. So you see how the criterion goes from 78, all of a sudden it drops down, and here we're pretty much done. It doesn't change very much anymore. So this is these are the clusters of, and actually I forgot, but yeah. So there was a southern south effect, see? So most of the south is together, and of course we have the south dummy, which we can put in here, and we can run it again. There's the south, there's the dark points during the, so you actually can manually stop this. You see here when it kind of starts to stabilize and the points are just kind of jittery. They don't really move around anymore. So there's no point going all the way to the end. You can stop it and then save that result. Okay.